Hello everybody, welcome to our last Physics 206 lecture. Hasn't been the best semester with all the complications and trouble going on, but hopefully we can close out our 206 strong and learn some new stuff. Okay, so today is lecture number 30. We are on chapter 16. We're going to go over stuff that's on pages 408 to 413. No reading for next class because there are no more classes. Well, you'll have one more scheduled class, but I'm just going to send you a practice final to look at on your own, so there won't be a new lecture uploaded on Friday. And you also have your last homework due Friday, which is on this topic, is on oscillations. So today, we're going to talk about traveling waves, the general wave equation, the general wave equation is one of the most ubiquitous things you'll see in science and engineering, right? It's if you were to make a list of the 5 most important equations in science and engineering, this would probably be on there. Okay. And we're going to talk about musical tones. How does music arise from plucking a string? So we'll actually derive that from first principles, which should be kind of fun. So, we've been studying oscillations of mass on a spring, but I've been claiming that the math that goes along with that is very general and can be applied to a lot of different things. So today we'll see another example. So the example we're going to look at is if we grab a string. I wonder if I have a rope or a string around. Maybe I'm going to use my cell phone charger, right? If I hold this string taut, I can create a wave. That didn't work very well. I can create a wave, right, by moving my hand essentially up and down, and then the tension in this cord causes that wave to, go like travel down the length, right? This example isn't working out very well because this is kind of long and stiff, but if I'm sure at some point you've picked up a rope that was on the ground and done that, and you see a wave move down the rope. So let's draw a picture. Okay, we got a person here, and they've got a rope attached to a wall, and they go like that, right? And we see that they're moving their hand up and down. And on this rope, we see sort of a wave that travels that way. Right? And if this person keeps doing it, right, if they don't just do one thing, if they do that many, many times, basically they're creating sort of a sine wave or oscillation. So that would look something like this. Okay. So this should be starting to look familiar, and it looks a lot like the oscillations with respect to time that we get for a mass attached to a spring, right? So we saw functions that looked like this for the mass on the spring, but that was position of that object as a function of time. Here we have 2 positions. We have the y direction and the x direction, and this thing moves as a function of time, right? So now we're adding another dimension, essentially, right? And these waves will move to the right in the same way that this one moves to the right. So the farther out you are from the original equilibrium position, right? The equilibrium position is just here. The farther out we are in either direction, right? You're going to add more tension, right? That you're going to feel laterally in this direction. So if I displace, just to drive this point home a little, if I displace my anchor point, my hand, from equilibrium, the more I displace that end of the rope from equilibrium, the more tension that's going to put in the lateral direction, in this direction, on the rope, right? And the segment's next to where my hand is, and that's what's going to pull the rope up and cause it to move up, and then pull the rope down and cause it to move down. And that's a bit like the restoring force of a spring, right? As I lift the rope up this way, that's going to be increased tension in the rope, and that's going to want to pull my hand back into the direction towards the equilibrium, and the same when I go the other direction as well. So that's a bit conceptually why this is like a mass on a spring. So now let's put in the math. Okay, so we're going to zoom, I'm going to put in some labels first. Right. This is the y direction, this is the x direction, pretty standard. And what we're going to do is we're going to take a little slice, of this rope and examine that in more detail, right? So we're going to blow up this slice and look at it. And what we'll look at here, we've still got our x and y. So, so this kind of looks like that. So we have a gentle slope upwards, right? So we're taking this and expanding that x direction out. So this is, we can see now more the slope of this. And this little sliver, we're going to call that delta x. So this down here, this is also delta x. Okay. So we're going to treat this small segment of rope as an object. Okay. And if we're just treating this segment of rope as a whole, this whole thing is an object, now we're going to look at the tension forces on either end of the rope. So we'll have, it's a little tricky to draw, so give me a moment. You know what, there's no reason for you to watch me struggle to draw this. I'm going to pause it. Okay, we're back. So I drew it a little bit better, I think. So what's going on here? So this is the segment of string, which we're going to count as a small object subject to tension forces, right? So I labeled this end of the rope as x prime. This end is x prime plus delta x, where this delta x is this small little segment here. And if you've been paying attention this semester, you know that when I'm talking about small little things, right, that's eventually I'm going to start talking about infinitesimals and derivatives and stuff like that. So we have a tension force on each end of this rope. This is TL down here, that's the tension on the left part of the string, and TR over here, the tension on the right part of the string. And then we decompose both of those forces into its components in the x and y direction. So we have this component here, the Tx component, which is going to match with the Tx component over here, right? This goes with this arrow, this dashed line I drew in because I ran out of space, and this board is too small, really, to do some of these calculations. So this one then is Tx. Over here we have a Ty, and that Ty is evaluated at x prime, so at this point here, and this Ty over here is evaluated at x prime plus delta x. So this distance over here, right, plus that x prime gives us the y component at this point, right? So this would be the y component over here at x prime, over here, this guy, and then the x, or the y component at x prime plus delta x, which is over here. So what we're going to do is we're going to treat, like I said, this segment of rope as one massive object, and what we're going to do is we're going to apply Newton's second law to that. So we're going to apply force equals mass times acceleration, and the mass is just going to be rho delta x, right? The density of the rope times the length of that segment, which we've labeled up here, so that rho is density. And then rewriting this equation down here, the acceleration in the y direction is going to be equal to the second derivative of d, and I'll talk about that in a second, with respect to time, and d is going to be evaluated at x and t, or rather be a function of x and t. So what this d is, this capital D, that is what we define as the displacement. Right? And we talked about a displacement in the beginning of the class as just being a definition of a length or a motion, right? But this displacement here, this specifically means the displacement in the y direction, right? So this small segment of rope is going to move up and down as these waves travel fast, and the reason, or travel past, and the reason is that we're going to have these two counterbalancing y tension forces, right? The bit on this side wants to pull that rope up, the bit on this side wants to pull that rope down. So the acceleration in the y direction, how it moves up and down, is just by definition the second derivative with respect to time of this displacement. So over here, right, we could define this as being that displacement. Okay? And it's a function of two variables. It's a function of how far along we are in the x-axis, because we're talking about, okay, this little tiny segment at what point along the x-axis. And of course, the motion of that is also going to depend not just on the physical distance in the x direction, but the time, right? As we go up and down like that, as we create those waves, right, they move both in position and in time. But, of course, like you would expect, this is a piece of rope, or we'll see it has a more general interpretation later. This little piece doesn't move this way, right? It just goes up and down. It just looks like a wave moves to the right, but really nothing is moving to the right. The rope is staying stationary in the x direction. It's the individual little bits of it are moving up and down the y direction. That's what it makes it look like. There's something moving in the x direction. So we're going to assume that this rope doesn't stretch or compress very much, and that we're going to have each one of these little segments along the rope, it's not going to move in the x direction. And because we're going to say it's not going to move in the x direction, well, then we'll know that these tx's cancel out, right? Because they cancel out, we know that we're not moving in the x direction. We're just moving in that lateral y direction. Okay, so that's an important point. This d is a function of x and t. That tells us what the shape of this wave is. Okay, we could call this the wave function. It tells us how that wave looks like in space and in time. Okay, and for those of you who are who have gotten to this in calculus, when I write this d here, what I really mean is the partial derivative. But since we never talked about partial derivatives in this class, I just kept it as this d. So if you know what this means, then what I'm really talking about here is a partial derivative. If you don't know what this means, just forget it. It's not important. You'll learn it later. Okay. So we know that our F net is just going to be equal to those two tensions, the tension on the left, the tension on the right. I've already claimed the x tensions are going to cancel out because the rope's not moving in the x direction or stretching or compressing, we assume. So our F net in the y direction is going to be equal to Ty x prime plus Ty x prime plus delta x. Okay. So what we're going to look at next, I wish I still had the picture, but what we're going to look at next is the slope, right, of those tension forces, which is the same as the shape of the line, essentially, right? That shape of the line is given to us by the geometry of how steep that rope is curved at in that little tiny segment. So that slope, right, that rise over run is going to be an important quantity. So this is the rise over run of the rope, which again is the same as the tension forces, okay, the Ty and Tx. Right? Just to be clear and say this maybe one more time, the geometry of the tension forces is given solely by the shape of the rope, which is why we can write a rise over run of the shape of the rope, and then the next step I'll write down that these are the tension forces in the x and y direction. So that rise over run is equal to Ty at some x position. So this is general, it doesn't have the prime on it. So Ty at some x position divided by the Tx. And we are assuming that the Tx is the same everywhere for the reasons we were just talking about. Okay. And now, it's pretty easy to see that this is just that d, the first derivative of that displacement d, right? Again, the tension forces are the same as the shape of the rope. This is how we can see the shape of the rope, and this is how we can see the tension, so they're the same. They're both equal to the slope of the object. So this displacement up or down on the rope is a function of position and time. And so we just invert this equation, right? So we set this guy equal to this guy, and then we'll multiply through by Tx, and we get Ty, and now I'll write in that x prime, and this is equal to negative Tx d x prime time, right? So this is general and now this is specific, by dx. Okay. And so what this actually is, for those of you who are aware of the calculus subtleties, this is d by dx of d evaluated at x prime. Okay, so that's what that is. So we would take the derivative and then plug in the x prime. And this negative sign comes from the fact that, now that we make this the specific case, we know that those y components are going to be pointing in opposite directions, because on this side of the rope we have the tension pointing up this way, this side of the rope we have the tension pointing down, so this negative sign takes that into account. Okay. So we write this same equation again, and now we have Ty is x prime plus delta x. So we're writing this equation for each side of the rope, right? So this is the negative sign, so it's the left side, and now this will be the right side, right? And then you can see that also because I have the plus dx there. This is Tx, right? Opposite sign from this one. dd x prime plus delta x t, evaluated the same way this one is, but now with an x prime plus delta x and by dx. Okay. So now what I want, I'm going to add these two together and get this F net, right? This gave us the slope at each of those points, the left and right point, either the left or right point, This is specifically the left point. This is specifically the right point. And now to get that F net, we add these two forces together. So we're going to add this Ty, and that Ty like we add the TL and Tr there. So I'll just erase everything because there's much more to write. So now that F net of Y is equal to Tx times the quantity d x prime plus delta x dx minus d, oops, should be also a t there, comma t, minus d x prime t dx. Okay. So to continue, you need to use a little bit of a trick, okay? And that trick is that we're going to define a new function, right? Given by the script f, script lowercase f, and we're going to make this general, so we're going to say just some q, right? Some interior of that function. So that's going to be just some position, we're not going to define it yet. And this function is defined as the derivative of a displacement. Okay? So we're just saying that everywhere we write f, which is some function, what we really mean is the first derivative of the displacement with respect to position. Okay? So we're just taking those derivatives and defining them as a function, and we'll see why this is a good trick in a second. So we go back to our equation of motion. So our force equals mass times acceleration. So we have rho delta x, that's our mass, and then our acceleration is the second derivative of the displacement with respect to time. And then this is equal to the force, of course. We have Tx. So if you hear that banging, I'm sorry, they're renovating the apartment next door. There's nothing to be done. Sorry. Where was I? Why did I draw that? Strange thing. Okay. So B actually, this is a bit long. So this is equal to Tx dB x prime plus delta x dx minus d x prime, got the t again, t minus dB x prime t dx. So now we're going to do the thing that we often do in this class. We're going to take that small delta x and take it to an infinitesimal. So the way we're going to take that delta x to an infinitesimal is we're going to take the limit. So hopefully you all are familiar with limits by now. So now we're going to rearrange this and take the limit. So we have rho divided by Tx, second derivative of the displacement with respect to time, equals limits, delta x goes to 0. And now we're going to use this definition of this function over here to write these derivatives. So now we have function x prime plus delta x. I'm going to leave off the t. minus f of x prime divided by delta x. So I want you to look at this function for a second, this expression, and you should either immediately recognize this or have the creeping suspicion that it's familiar. So think about that. Pause. Okay, so what this is, actually, is our definition of a derivative. Okay, we have a function evaluated at one point plus some delta x minus the function evaluated at the original point. So evaluated at x plus delta x minus the function at x prime divided by the distance between those 2 points that we evaluate the function at. Right? This is the definition of the slope. This is the definition of the derivative, right? When we take that distance to 0. So this is our definition of a derivative, which means that with this, excuse me, this is the derivative of this function f, right? Which means that since this function is a derivative, this guy here in total is the second derivative. We're taking the derivative of a function that's already had a derivative taken of it. So this tells us that this whole thing is now the second derivative with respect to position. Okay. So what we get is rho over tx, second derivative of displacement with respect to time, equal to the second derivative of the displacement with respect to position. Okay. So it's kind of a weird equation. We have on the one side the time derivative, on the other side the position derivative, okay? And then multiplied by this guy over here. Okay. So it's a differential equation. Let's solve it. We're going to use guess and test like we've been doing. So our guess is going to be d as a function of x and t is equal to a sine 2 pi over lambda x minus omega t. So the book calls this 2 pi over lambda, they call that the wave number k. Wave number. So I'm just going to leave everything in terms of lambda, the wavelength. But this is also standard using the wave number, which is just the inverse of the wavelength times 2 pi. Okay. You'll see this around. So we have 2 bits of the interior of this function. We have a space bit, right? It tells us how the oscillations in the x direction work, and we have a time bit, which tells us how the oscillations with respect to time work. Okay. And this is all in the interior of this sine function. I'm not going to plug it in and prove it. I'm not going to do the same thing I did the last 2 classes, actually do out all the guess and test. By now that should be fairly familiar, and this doesn't work in any weird way, right? And I've already plugged in the correct constants instead of leaving them general and solving for them later, right? These are already the correct constants. This is the solution, okay? We're not going to prove it, but believe me or do it out yourself, okay? So this gives us, if we plug in this equation to our differential equation down here and solve it, we get the requirement that omega squared equals the tension, right? We're just going to call this now the tension in the string, the total tension. Okay? So it's just the tension in the x direction divided by rho times 2 pi divided by lambda squared. So, as before when we looked at these guess and test constants, right, that we get from doing out the differential equation, we were able to already get, just from the definition of these constants, some physical insight. So we can do the same here. So just rearranging this slightly, Ts divided by rho equal to lambda omega divided by 2 pi squared. So if we want to know what the speed of a wave is, right, that's how often the peak passes, the frequency, times the wavelength, right? How long the distance is between each of those points, right? So if we want to know the speed of a wave,